Hi class, let's talk about solution spaces for homogeneous linear recurrence relations. Think about the Fibonacci numbers, where the nth term is the sum of the previous two terms. So fn is equal to fn minus 1 plus fn minus 2, where the first term is 0 and the second term, f1, is 1. The problem with recurrence relations is that they are defined recursively. So if you want to know what the nth term is, you have to calculate and know previous terms, and those terms depend on terms before that, and those terms depend on terms before that, etc., etc. It can be really time-consuming to figure out the term that you want. What we want is a solution for recurrence relations. Definition. A solution for a recurrence relation is a formula for the nth term of the sequence defined by that recurrence relation given the initial condition. Ideally, we don't want this formula to depend on the elements of the sequence. We want to unravel the recurrence relation. Let's talk about what something like this might look like. Example. Let's discuss the recurrence relation an is equal to 5 times an minus 1 minus 6 times an minus 2. An is equal to 3 to the n or an is equal to 2 to the n are both solutions. What do I mean by this? Well, let's explore the idea that an could be equal to 3 to the n. This means that 5 times an minus 1 minus 6 times an minus 2 is going to be equal to 5 times 3 to the n minus 1 minus 6 times 3 to the n minus 2. If we do the algebra, we end up with 3 to the n, which is an. That is, an is equal to 3 to the n satisfies the recurrence relation an is equal to 5an minus 1 minus 6an minus 2. Similarly, we can explore the idea that an is equal to 2 to the n would also satisfy this recurrence relation. 5an minus 1 minus 6an minus 1 would be equal to 5 2 to the n minus 1 minus 6 2 to the n minus 1. Doing the algebra, that gives us 2 to the n, which is an. So 2 to the n also satisfies this recurrence relation. That is what it means to be a solution to a recurrence relation. Before we start talking about how to find these solutions, it's actually going to be helpful for us to understand the structure of the solution space. Let me tell you what I mean. Let a sub n be equal to some function g of n. Suppose that's the solution to a second-order linear homogeneous recurrence relation. So that recurrence relation would look something like this. An is going to be equal to s1 times an minus 1 plus s2 times an minus 2, where s1 and s2 are some real numbers. So this is a recurrence relation that's homogeneous and linear in the two previous terms, an minus 1 and an minus 2. What this means is that gn, this function in n, satisfies this recurrence relation, just like so. Fact: constant multiples of solutions are also solutions. If an is equal to some function g of n is a solution and c is some real number, then an is equal to c times g of n is also a solution to the same recurrence relation. Let's talk about how this would work. So if an is equal to s1 times an minus 1 plus s2 times an minus 2, and gn is the solution for that, then gn is also equal to s1 of g applied to n minus 1 plus s2 times g applied to n minus 2. Then if we multiply through, then we get the equation that shows that c times gn also fulfills this recurrence relation. Fact: if an is equal to gn and an is equal to some other function h of n both satisfy the recurrence, then their sum is also a solution for the recurrence relation. Let's just write down why this works. If an is some recurrence relation and both hn and gn satisfy it in this way, then if we add these two things together, we'll get hn plus gn also satisfies the same recurrence relation. Putting this all together, this is what we have. For linear homogeneous recurrence relations, the solutions form a real vector space. Of course, this means that it's closed under addition and scalar multiplication with real numbers. The dimension of this vector space is going to be the order of the recurrence relation. Here's an application of what we've just learned. We expect the solution space of this recurrence relation, an is equal to 5an minus 1 minus 6an minus 2, to be a vector space of dimension 2. Why? Because it is a linear homogeneous recurrence relation of order 2. Since we've found two linearly independent solutions, an is equal to 3 to the n and an is equal to 2 to the n, and we have just a two-dimensional vector space, these two solutions should form a basis of that vector space, and we expect all solutions of this recurrence relation to be linear combinations of these two. That is, all solutions of the recurrence relation an is equal to 5an minus 1 minus 6an minus 2 will have the form an is equal to c1 times 3 to the n plus c2 times 2 to the n, where c1 and c2 are real numbers. One can already appreciate the applicability of understanding that these solutions will form vector spaces. Next class, we're actually going to figure out how to find the individual solutions, as in how did we come up with the 3n and 2n to begin with.